so sorry. Okay, so we'll just say that r cube over, okay, so the part one was that r cube over t squared is equals to the gradient of the graph, which is basically constant. And then moving on to part two. So this is something that we have defined where the star H has a mass m and it has a planet X with radius r and mass m. So these are basically some of the variables that we have defined in this. So since we are assuming that X is in circular motion, so what we're going to do is we are going to write circular motion, centripetal force is equals to the gravitational force. Okay.
Yeah.
So, okay, just copy the question. So, this is the graph, okay? So
Yeah.
I'm not going to tell you what I'm going to do, but we will just see that how this working sort of relates back to this graph. Okay, so the formula for the centripetal force is mv squared over r. So, and the formula for the gravitational force is g, which is the gravitational constant, m times m divided by r squared. Is it okay?
Yeah.
So, so that's now what we're going to do is we're just going to rearrange, since see now the mass of the planet X is cancelled and we're going to cancel r and r. So this is going to become v squared is equals to the g m over r. Okay. Now remember, we have to find the value of m because the value of m is what we have defined the mass of the star H, and g is a constant here. R, we don't know what r is and we don't know what v squared is, so we have to relate this to something that sort of makes gmm equals to that. Okay, now let's look at here. What's v? I haven't defined v. What's v actually is?
It's the velocity.
Yeah, it is the centripetal circular velocity, or just write velocity just for now. Okay, so
Okay.
this velocity can be written down as 2 pi r divided by t. So what's the 2 pi r now? This 2 pi r is basically the circumference of the orbit of planet X. Okay.
Yeah.
And this t is the time period.
Yeah.
Okay. So what I did here is I defined velocity to be equals to the distance, sorry, distance over time. So what I did is I wrote this velocity. I'm just gonna change this so this is also so that doesn't confuse you. So I just wrote speed because it's moving in a circle. So we don't need the momentarily speed. So what we're gonna do is we took the distance. Now what's the distance? We took the distance that the planet covers in one orbit. So the distance that the planet covers in one orbit is equal to the circumference of that orbit. So let me just explain it to you a bit. So let's say you had, this is the planet, this is the star H, and you're defining this blue thing. The blue is the circle. This is the orbit of orbit of planet X. Okay, so the distance that this planet on this orbit covers is equal to the circumference of this orbit. So basically this is this if this blue dot is the planet X, then the total distance that this planet covers in one orbit is equals to the circumference of this orbit. Okay. Okay.
Yeah.
So I wrote distance is equals to distance of one orbit, and I wrote time also. Obviously we took for the distance of one orbit. Oh, I'm sorry. We wrote time to be equals to the time of one orbit. Okay.
Yeah.
So now what's the time of one orbit defined as? How much time? The time of one orbit is actually defined as the time period. Okay.
Yeah.
So this can be written down as T. So that's how I got my result, which was V is equals to 2 pi R over T. Okay. So you understand this? So what I'm going to do is I had a previous result of V squared is equals to G times M over R. What I'm going to do is I'm going to substitute, I'm going to plug this result of V in this equation here. Okay. Let's see what this becomes. This will become 2 pi R over T whole squared is equals to G M over R. Okay.
Yeah.
Now, this is 4 pi square R square divided by T square is equals to G M over R. So R cube over T square is equals to G M over 4 pi square. You see this result? Do you get this, like how I got here?
Yeah.
Okay. Now, look what I defined when I actually wanted to do part one was the reason that I did part one first was that I wanted to tell you that this result. In part one, I told you that R cube over T square is basically the gradient of this graph.
Yeah.
Yeah, so this is part one. Can you see my cursor?
Mm-hmm.
So in part one, when the question asked what aspect of the graph sort of tells you what what I'm sorry, just let me read the question. What features of figure 4.1 support the view that Kepler's third law may be applied to the system? So we said, okay, so the Kepler's first law says, the third law says that t square should be directly proportional to the cube of the radius. This means that t square over r cube should be a constant. And same goes for r cube over t squared. So it isn't different, this is reciprocal. So the reciprocal of a constant is also a constant. Okay.
Okay.
So this is what was the feature that was in the graph, which can tell me that, okay, this is this in the system we can say that the Kepler's third law applies. Okay.
Yeah.
So what we're going to do is we're going to take this result, which was r cube over t square is equals to gm over 4 pi square, and we are going to just write this t square is equals to the gradient of the graph. So what we're going to do is write gradient of the graph is equals to g times m over 4 pi square. Okay, now look at what we found. G is a constant. We know the value of g. We know the value 4 pi squared is also a constant. We can find this result since we have the graph. We just use the formula of the gradient and then find this result for the gradient, and then plug all these values back in this equation to find the answer, which was the value of m, which I have already defined as the mass of the star H.
Yeah.
Are you following me on this?
Yeah.
Okay, let me just copy the graph here as well. So this is my graph. I'm gonna make a triangle. Did you make this graph yourself or was this printed?
It's printed.
Oh, okay, then fine. So we're just gonna take a triangle that covers a larger area of this. So just to this sort of increases the accuracy. So we're gonna take this point and we're gonna take this point. And what we're gonna do is we're gonna draw a triangle to find the gradient. So this, and let me just draw this here as well. So we took this point and okay.
Yeah.
So what's the length of what's the height of this? So this is one, 2, 3 boxes up, 1, 2, 3 boxes up. So this thing, so this, how much is this? 10, 12.5. Okay, so each of this is 5 divided by 20. Sorry, what's 20 divided by 5? So each of this is 0.25, 12.5, 12.5, 13, 13.5. So this is 14, and this is 2.5, and this is 0.7, and this is 4. So the length, this length is 3.3, and this is 12 and 11.5. So my gradient is equals to 11.5 divided by 3.3. This comes out to be 11.5 divided by 3.3. So this is 3.485. So what we're going to do is write 3.485 is equals to G times M over 4 pi square. M is equals to 3.485 times 4 pi squared divided by G. I'm just going to write the final value now. So this is equals to 2.06 exponent 12 kilograms. Did you follow this result?
Wait. The answer is 1.97 times 10 to the 30.
Is it? Wait, did I? Oh, okay. Oh, I know what was there. So the gradient here is not what we missed here was these units. So sorry, we didn't read this units. This and this. I'm not able to see this here. So okay, 1016 and 1034. So y-axis was 11.5 into 10 raised to power 34 divided by 3.3 into 10 raised to power 10 raised to power 16. Okay.
Yep.
So what we're gonna do is we're gonna write 34 minus 16. We're just gonna multiply everything by 10:18. So this will get multiplied by 1018, and this will get multiplied by 1018, and this will be 2.06 exponent 30. So it's approximately the same thing. It's just a plus minus because of the gradient we found. Maybe you can find it better with when you have it on the paper, the graph. On the whiteboard, it sort of becomes a little messy.
Yeah.
Okay.
Yeah.
Okay.
There's also another question.
Yeah, just send me the question. Did you follow this result? I'm sorry, I just took so long because I had to, write everything down and explain it.
Yeah, it made sense. In the equation booklet that I get given, it actually already has the equation t squared equals 4 pi squared over gm times r cubed. So I don't think you need to, would I still have to derive it, or would I just use it directly from the booklet?
So if it is given in the booklet, then yeah, sure, you can do it because it's a 3-mark question. I don't think you need to do everything. And this is a pretty known result. So the reason that I actually define you is how by if you sort of know where the formula comes from, so you don't have to remember it. You just know where it comes from. Okay.
Yeah.
So you know how this result r cube is equals to gm times gm divided by 4 pi square times t square is coming from.
Okay.
Okay.
Yeah.
And so you want me to do part B 1 and 2?
Yeah, part A is fine.
Okay, in science fiction movie, a spaceship approaches Benzor has just the enter. Okay, so the first part is pretty much theoretical. So, what they're saying is, let me just try to draw like a how a planet or an object looks like. So this is a sort of a planet, although it looks like a ball. Like this is a planet, okay?
Yeah.
And say these are the poles of this. Now, the way like to understand how your Earth is moving is to hold like if you can hold like you can, if it's possible for you to hold a pencil in front of you. So I'll just show it to you if I can. Just wait. Okay. Can you see my video?
Yeah.
Okay, so just imagine this pencil to be a line where each end, this end is the North Pole and this is South Pole. So this is South Pole and this is North Pole. The way the Earth or any planetary object sort of revolves around its orbit is by actually revolving like this. So you have like a pencil in front of you, so it will just be rotating like this. So to enter a stationary orbit right above the South Pole, what would require for this to be at this point is to be stationary. So if it's anywhere here and I'm a geostationary satellite, so I'll have to be moving with the same speed uh, as same speed as this pen is revolving around. So like if I'm following this button, so if you can see this button, like if I have to follow, if I have to be right above this point, so I'll have to be in a stationary orbit already to be geostationary right above this. Okay. Now,
Yeah.
okay, do you are you able to follow this? I can explain it again if you want.
No, I understand.
Okay, so to enter a geostationary object right above this South Pole, what would require is you have to be stationary at all times. So you won't be moving. You'll just be having you just be sort of just have be stationary. Now, what happens is when you enter the orbit on a circle, the reason that you keep moving is because you don't want to get crushed in, get sucked into the planet. So if a geostationary satellite is right above the South Pole, that would mean that this geostationary satellite, if the tip of my finger is the satellite, this finger or this satellite would have to be stationary right above this South Pole. So what our knowledge of physics says, that it is impossible for us to be stationary in an orbit of a planet or a large object, because the gravitational forces act in, and they will suck you into the object, and the satellite basically will then crash into the planet. Okay.
Okay. So it's impossible because the gravitational field of the planet
So
will.
I'll just write it down for you. It's impossible because for a geostationary satellite right above the South Pole, the satellite would have to be stationary. Okay, so if I'm talking about a geostationary object, although when we talk about the geostationary object, we're talking about the perspective of a person standing on the surface of the planet. But here, when I say that the satellite would have to be stationary, I'm talking about from the perspective of the person on the satellite. So even that person on the satellite would not be revolving around. Okay.
Okay. So geostationary orbit is not actually stationary. It's just they're moving at the same time.
Yeah.
I mean,
So,
yeah.
so it's basically like I showed you. So if this is the pole, so this is the South Pole, and I'm following this button. So you see this button on this pen. So what I'm doing is, if to be right above this object, I'll have to move at the same speed as this button is revolving. So like this. So I'll have to follow this constantly, so that whenever anyone on the surface of the planet sees me, it sees me that I'm right above the sky. I'm actually stationary because I'm not able to see it from there. Okay.
Yeah.
So would have to be stationary. In that case, gravitational forces will pull the satellite. Something wrong with satellite towards the planet, causing it to crash on the surface. Okay.
Yeah.
Do you get this? This is B part 1.
Yeah, I get. Yeah.
Okay. All right, let me read part 2. So calculate the radius of the. Okay, so the next part is pretty much easier. I'm just going to copy this down here. So okay, now we know that Benzor has mass this, and in the question above, they also told you the time period, which was 1.2 exponent 5 seconds. Yes. Okay. What we're gonna do is we're gonna use the result that we derived in the previous question that we did. So what I'm gonna do is I'm gonna take this result and copy this down here. So r cube over t squared is equals to g m over 4 pi squared. Here g is a constant. We know the value. 4 pi squared is also a constant. We know the value of 4 pi squared. M is given to be 8.9 exponent 25 kilograms. T is given to be 1.2 into 10 raised to power 5 seconds. Everything is basically given to us. What we don't know is this R. Okay, so
Yeah.
we know that what T is, we know what M is, we know G, and we know 4 pi squared. So I'm just gonna plug in the values now. So this is R cube over 1.2 exponent 5 squared is equals to G times M, which was 8.9 exponent 25 divided by 4 pi squared. So R cube comes out to be, let me use the calculator. So G times 8.9 exponent 25 multiplied by 1.2 exponent 5 pi squared and 4 times pi squared. So R cube is 2.17 into 10 power 24 meter cube. So R is the cube root of this. So I'm just going to find the cube root of this answer. This comes out to be 1.29 exponent 8 meters. Okay.
Yeah.
Okay. Do you are you able to like follow this?
Yeah.
Okay. So yeah, this is pretty much the question. Do you have any other question?
No, that was the last question.
Okay. So like, would you like to like study something, because we have like 10 minutes on our class left?
We can go over circular motion.
Circular motions in the perspective of like the gravitational force, or like circular motion in general?
Like more of the gravitational one.
Mhm. Okay, well, let's just talk about circular motion. Okay. Now, the idea behind the circular motion is that I have some sort of like a string, so like this mass, and I'm sort of rotating it around the circle. So if I'm rotating it like this, that means that if this is my hand and I'm rotating this, let's say this line is the mask. If I'm rotating this in a circle, so I'm sorry, it's a very bad circle, but you know, get the idea, okay?
Yeah.
So, okay. So if this is the line, this line is the mask and this is following this track, so the circular track, the idea behind circular motion is that the centripetal force is always acts towards the center of the circle. So if I am rotating this mask around my hand, so this means that the centripetal force is basically towards my finger, so the point that I'm holding the other end of the mask. Okay, so now if we talk about objects like bigger objects like the two planets orbiting around each other, like the moon is orbiting around the earth and the earth is orbiting around the sun. So this field of study also is the Newton's law of gravitation says that the force, when there are two masses, they always attract each other, and by the force that the objects attract each other towards is directly proportional to the mass of the product of the masses of the two objects and the square of the radius. I'm sorry, not the square of the radius, just radius. So sorry. Okay.
Okay.
So this is what no,
Wait, is
square.
it not? Yeah, yeah.
Yeah, it's a square. Sorry, I just sort of messed it up with the gravitational field. But okay,
Mhm.
so the idea of the Newton's law of gravitation is also the same, that when if this is like this pen is in orbit around this finger, which is a star. So if this is orbiting around this like this, so that means that there's a force of attraction between the tip of my finger and this pen that is causing this planet, or in this case my pen, to go in circles around my finger. So when we say that they're moving in circles, we define that force, we assume that the orbit is circular, but in real life it's not circular. It's actually in something called an ellipse. I hope you've learned the Kepler's first law.
Yeah.
Okay, so but in general, and like in your syllabus, at least till your level, we assume that this is the objects are orbiting, the planets are orbiting each other in a circle, which means that I can equate the centripetal force by the gravitation force. Okay, and in your syllabus at your level, this is the relation that's used the most. So you saw in the last two questions that we did, we've derived our formulas using these two relations. Okay.
Yeah. I have a question. It's not a written question. It's just that so if there's two planets, so a big one and a smaller one, so the force on the bigger one will attract the smaller one. Does the smaller one also attract the bigger one, or because it's smaller, nothing really happens?
Oh yeah, so the thing is that this force isn't this force is not just that force. So this isn't only relating how the gravitational, we're not talking about the strength or the inertia of one planet, we're talking about the resultant of this force. So in general, we know that if there's one force that acting towards one side and there's another force that acting towards another side, and this force is bigger, so this object will move towards the left, move towards the bigger force.
Mhm.
Okay, yeah, so this is the basic concept of, this is the force that's applied there. We're not talking about a single force. So this force is not only from the bigger planet. So that's the general idea, because the reason that the bigger planet has the smaller planet is attracted towards bigger planet is because the smaller planet doesn't exert that much force. The Newton's third law of motion is there, but the reason that it is moving in circles is because there's a resultant force that acting towards the center of the planet, in the center of the bigger planet, or basically. Okay.
Okay. Yeah.
So I hope it's, yeah.
Yeah. Also, when so the moon orbits the Earth, but why does the moon not get, so it's attracted to the Earth because the Earth has a greater mass, but then why does it not keep going in? Like, why doesn't it just collide with it? Why does it go round?
Okay, so the reason that is because the moon itself has its own motion. So there is no such thing there. So if there was a solar system where there was only Earth and only moon in there, so it would just collide in. Yeah, that's correct. But the reason that it keeps on revolving is because there are other planets as well.
Okay. So the other ones also attract the Earth and stuff.
Hmm.
Okay.
So it's, the thing is that the velocity of its rotation, the moon's rotation, is just causing it's perfect in a way that it's saving the moon to escape from the Earth's object, and it's also perfect in a way it's not causing the moon to just like crash into the Earth. So that's the idea. So if even if the velocity of the rotation with which the moon is rotating around its center was to be a greater than or less than greater than what it is right now, it would then just crash in the Earth. Or if it was slower, then it would just escape. Okay.
Okay. Yeah.
All right. So are we clear on this?
Yeah.
All right. I think so this probably ends our class today, and I hope like